Hello everyone. So I'm Irene Raisa Kameni. I'm a machine learning researcher. Now I'm a data science at Tesho, a matrimonial company here in Douala. So I'm going to present today the principle of language modeling and transformers in NLP. I didn't take in consideration any prerequisites. So whatever the background you have, I think you're able to access this course. So what is language processing? Language modeling. Usually, language is a method of human communication, and it is characterized by a text. So during this talk on language modeling, the first part, I'm going to define what is a text, language modeling in question, how it works, and some of the application that use language modeling. So what is a text? A text is a sequence of tokens. And a token can be a character, a word. A text is composed of some character. You can have a word, phrase, some sentence, a paragraph, a document. So inside the document, you have all these. You have all these tokens. So a word is a meaningful sequence of character. For example, you have a AI in Cameroon. That KmerAi AI is the community of.
Irene, I'm really sorry to interrupt you. Sorry, there was one participant was asking if the presentation can be put in full mode, but since you are using a notebook, maybe if you can increase the presentation, that would be nice. Yeah.
Okay.
Yeah, that's better. Thank you. Sorry, you can continue.
Okay. So I was saying, what is a word? A word is a meaningful sequence of character. We have AI in Cameroon. It is composed of some token, which here is a character. You have AI in Cameroon, can be written on each character. Even space is a character. So language modeling in question is the probability given to a token. Suppose you have a sequence of token. Language model estimate probability of this token, of each one of each token from this text or the file. So, like I said, language modeling estimate the probability of a token of an upcoming token. You can want a probability of a token knowing the past token. It can be a unigram or a bigram. I will illustrate it below. So how to compute the probability? You may want the probability. The sequence can be independent or not. So it depends on what you are looking for. There's this many way to compute probability. It can be done by counting the number of times of a sequence, number of times a sequence of token occur in this data set. That method is called count-based language model. I give some in that example of, let's take a few examples of a data set. The second one, I'm at Buea, Cameroon. I may want the probability of Cameroon knowing that I'm at Buea. So using the count-based language model, on this sentence, you have a half. The probability of knowing Cameroon, knowing I'm at Buea. But one limitation with this method arrives when you have a long sentence with not enough statistics. So to fix this issue, we truncate the pass to a fixed size window. This is what I was saying previously concerning the n-gram model. So n here refers to the size of the pass. On n-gram model, when n is 1, you have unigram. When it's 2, you have bigram, and 3, you have trigram, so forth, so on. So when you have a bigram, the probability here it will be W1, W2. So now it will be the product of probability of one knowing the previous one, just the directly the one coming before the token you are looking the probability. So n-gram can be good enough in some case, but n-gram cannot capture long-term dependency. And to fix this issue, we use back-off interpolation, for example. Here, what we call back-off is use trigram if you have enough data. If not, you use the bigram. You can also use interpolation with the mixture of some n-gram, like you can use trigram, bigram, and the unigram. You mix the tree. That is what we call interpolation. You can go on this site to know more about the n-gram model. Now, the number of parameters grow with the window size of n-gram. And you have problem with memory. Sorry. Because the memory of the pass limited to n-gram window size, you have to deal with the number of parameters. That is where the recurrent neural network comes to our rescue. What is recurrent neural network? It works on the principle of saving the output of a particular layers and feeding this back to the input in order to predict the output of the layers. Sorry. So the recurrent neural network will create a few issues in the feed-forward neural network. It can handle sequential data. Also, it considers only the current input and cannot memorize previous input. So I was saying, RNN is an abbreviation of recurrent neural network. It comes to rescue because it can handle sequential data, accepting the current input data and previously received input. It can memorize previous input due to their internal memory. An illustration. Here you have a diagram of a neural network. This is fully connected, where between the input and the hiding layer, everything is connected. But you have the problem of long-term dependency. Now this is RNN. So here you can see the hiding layers. Before going to the second layers, you take the input. You take the input here, and here you have the hiding layers giving you the output. This one, all this one come back to the hiding layers, the second one, the second hiding layers, and so on. So it's not like the neural network where all the input fit into the first layers, and now it's the second layers that fit to the second one where everything is connected. On the recurrent neural network, I will repeat myself. It can memorize the previous input due to their internal memory. So it's accepting the current input and previously received another one. This is the current input, for example, and accepting the previous one. So now I will explain what is transformers. Transformer here is a deep learning model that adopts the mechanism of self-attention. I will explain what is attention, differentially weighting the significance of each part of the input data. So, like recurrent neural network, transformer designed to handle sequential input data, such as natural language, for tasks such as translation and text summarizing. However, the difference with the RM is that transformers do not necessarily process the data in order. So I was saying that transformers do not take in consideration the order of the input data. Rather, the attention mechanism provide context for any position in the input sequence. I will take a simple example. The way you say a sentence, it depends on the context on which you are saying it. So attention here, it comes to highlight some part of the text, which put it on the context. Later, it defines the context that confer meaning to each word in the sentence. So this feature allows for more parallelization than recurrent neural network, and therefore reduce the training time. The transformer in NLP is the novel architecture that aims to solve sequence-to-sequence tasks while handling long-range dependency with ease. The transformer was proposed in the paper, Attention is All You Need. It is recommended reading for anyone interested in NLP. The paper, Attention is All You Need. You have a diagram of attention where you have the input coming, and here you have what I was saying, multi-head attention. This is multi-head attention. During the encoding, where you have your layers, here you have your input. The head is here on the linear. Here on the linear, they take the W, the optimizer, the parameter W, and they apply it on every input coming previously before the encoding. And this is the number of that W parameter that we call the head. It can be 8 head. That means you will have 8 times 3 on this example. So the application, you have application on speech recognition, on optical character recognition, handwriting recognition, the context-sensitive spelling correction also, and on speech recognition. How do they use language modeling? Here, they give the ability to a machine to convert spoken language to text regarding to the sentence below. Coming from different countries, we have different accents, for example, and our pronunciation of words may sound differently. But using a probability of language modeling, it is more probable that you may want to say chocolate ice cream than chocolate ice cream. You see? So the probability of chocolate will be less chocolate ice cream is here. The probability of this will be less than the chocolate ice cream. And this, for example, the second example, you have I hate you, Jerry. It will be less than I ate a Jerry. Oh, machine. You have also machine translation. Here, it processed by which computer software is used to translate a text from one language to another one. For example, translating, you have Google Translation. It also uses language modeling. So in this process of translation, language modeling comes to the head by giving a more appropriate translation. So French people, we agree that agréablement surpris is more suitable than déçu en bien for pleasantly surprised. So that probability of déçu en bien, knowing pleasantly surprised, will be less than the probability of agréablement surpris, knowing that is pleasantly surprised. That is the translation. But you get what I mean. Now, on optical character recognition and handwriting recognition, optical character recognition is the recognition of printed or writing text character by a computer. This involves photo scanning of the text character by character. Sorry. So now I think you have Google Lens that extract the text from a picture, and you can have it put it on Google Word, for example. So here is optical character recognition. So knowing that there are letters and digits with the same or have the similar shape, for example, you have 0 and O. We use language modeling in this case to fix this. So using probability of these letters, sorry, we have move with 0. You have move with 0. And you have and will be less than move with the letter O. So here, the language modeling help optical character recognition to fix this kind of issue. Now, one of the applications, the context-sensitive spelling correction. So it's the task of correcting spelling error which result in valid words. It is very interesting to see what language modeling can do. Particularly is to have a context-related error. We may receive a message like, there are problems with this sentence, which here don't have a letter, and may not understand what the sender of the message want to say. Why each word of the sentence is well written and have a meaning, but together don't make sense. Once more, using probability of language, we are able to have a look at what the sender may want to say. So the probability of there are problems with this sentence will be less than the probability of there are problems with this sentence. No, now I give some example of the coding. You can import some package useful in language modeling. I define I define some character that I will use, and the file using here is Shakespeare input doc text. You can find it here on the Stanford website. So here now I define for example, the length of the shock. So as indicated by its name, it hides randomly a shock from a file. We will need it in the letter to illustrate how language modeling will reconstruct the file. For example, here, we are telling him from the length on the length of text where we want it to hide some part of the text. Here we use the recurrent neural network. On the initial function, we define the number of layers we want, the encoder, the decoder also. So the encoder here is the embedding, and I also record gate recurrent unit. The decoder is the linear model, linear function. On the forward, you have the decoder with the linear taken in the neural network module, and the output is, we used here the softmax function, log softmax function. So the function below here take as input a string and convert it into a tensor vector by converting each letter into a number. A number here corresponds to index of that letter in sequence of all characters and put them together. I take an example here of A, B, C, D, E, F. Here it convert each letter here into a number. So this is how it's presented. For example, A here is 10 and B is 11, just after 11, 12, and so on. So now we define the random training set. That function consists of taking the first length, the shock of the length of the shock, and the last one, -1. Here now we evaluate our model. So to evaluate our model, we here want to print the predicted one. I just want to make you in the context, because in the beginning, I said we want to add some part of the file. After, we want to reconstruct it, because hiding some part of the file, that file is the text file, of course, is the Shakespeare input. We want to understand some part of the text by removing. When I say just removing some and trying to reconstruct to know if our model is able to understand the meaning of the sentence, what we wanted to say. I can take a simple example. When you use your WhatsApp, sometimes when you write some text, before finishes typing, WhatsApp proposes you the next one, depending on where you started. For example, on my phone, if I say the grace of, you automatically say God, grace of God. So like I'm saying here, the premise string to build up hidden state. So what I show you on the diagram, it is what is done here. Now we want to know the concerning the memory, the part of the memory, know how many the time is taking to process. So to train our model, we define a function train. The function is giving the average loss with respect to the number of times we had a shock of our inputs. Here is optimize our W and compute the loss function. The loss function is the average loss. So when we use a model, our objective is that we want the loss to tend to 0. So on the step below, we go through thousands of iterations to evaluate our model. So here I take the number of epoch 1000. The decoder here is the recurrent neural network. It's what I'm using. I take like the optimizer, the Adam, and I'm training my model. The more you add the number of epoch, it helps your model to train well on this context. So I plot here how the loss function, the behavior of the loss function. Like I said, I want it to go to vanish. And here we can see that our loss function is decreasing. It's not yet at 0, but if it take more time. If I run the cell here, it will take too much time. When I say too much time, it's like 3 minutes. If I increase the number of epoch to 1000, for example. Okay, thank you very much.